All right, let's talk transferable energy. So during all this stuff, energy can also be transferred from one body to the next. Okay, without us humans, most of it is known as heat. Think of rubbing your hands and they get hot, right? Because friction causes your skin to lose energy to the environment, and then you feel this. You also feel this when something free falls. That's called air resistance. Or if something is going through water and you're losing, it's losing speed. That's due to water resistance. It's losing speed because heat is being released as the object is interacting with the water. Right? If I have my AC running in the summer and I open the door, I'll have my I'll have heat transferring from the outside into my car because heat flows from hot places to cold places. So I'm going to lose that cold that I just created by pumping all the heat out. Okay? I can calculate heat from MC delta T. There you go. Q is equal to MC delta T. M is the mass. Delta T is the temperature difference. And C is this thing called specific heat. Okay? And heat capacity or specific heat, it's the amount of energy that's needed to raise 1 gram of something 1 degree Celsius. What do I mean by that? Well, every substance has its own CP. You'll go look it up at a table, or you're given that in a question. Right? So water, for example, is 4.18 joules per kilogram per degree Kelvin, which means what? That in order for me to raise the temperature of 1 gram of water 1 degree, I need to put in 4.18 joules. That's it. That's all that means. It's just this fudge factor that makes it all work. Okay, so Q here is MC delta T. You can also say that enthalpy is MC delta T if it's under constant pressure. Okay, so don't worry too much about that. All right. So heat, this is how you calculate it, or if it's under pressure, under constant pressure, it's enthalpy, whichever one you want. And let's look at an example of how to do that. So I'm going to go over to my whiteboard here, and here's an equation. Here's a question. Calculate the heat involved in joules when 3 moles of water is heated from 10 degrees Celsius to 15 degrees Celsius. And I'm giving you the CP of water here is 4.18 joules per kilograms per Kelvin. Okay, so let's talk about how to do that. First of all, I am looking for heat, which is going to use this equation here. Q is equal to MC delta T. Okay, so I'm going to write that as the equation of use for me. MC delta T. All right, great. I have given you C is 4.18, so this is given to you. That's great. You need this in first of all, look at the units here. The units for this guy is joules per kilograms per Kelvin. And I want this in joules, meaning that I want to cancel out this kilogram and the Kelvin. Well, lucky for me, I have delta T, which is in Kelvin, so it's going to cancel out. And mass has to be in kilograms to cancel that out, okay? So that means to me that I need mass in kilograms of water. And I need delta T in K to cancel this out. And I'll get joules, and everyone will be happy. Okay, great. I do give you delta T. I give you that it goes from 10 to 15, but I give it to you in Celsius. So let's do that. So I know that my T1 is 10 degrees Celsius. And I can easily... If I want this in Kelvin, I'll remind you that T in Kelvin is T in Celsius plus 273. So therefore T1 is going to be 283 K, and T2 is going to be 288 K, because T2, by the way, was 15 degrees Celsius. So 15 plus 273, that's 288. 10 plus 273 is 283. Okay, so that means that my delta T is going to be T2 minus T1, which is going to be 288K minus 283K, and therefore it's going to be 5K. Hey, check this out. This is something that's always going to be true, but only for delta T, nothing otherwise. You always have to convert to Kelvin unless you're dealing with delta T. Check this. Delta T, if I didn't convert, in Celsius, I would have done 15 degrees Celsius minus 10 degrees Celsius, and I would have gotten 5 degrees Celsius. So it's the same. See that? So delta, which means delta T in Kelvin is going to be the same as delta T in Celsius. But otherwise, always convert to Kelvin. If you're not sure about this, just go with Kelvin. Just make sure you go with Kelvin. Okay, lastly, I need my mass here in kilograms. So mass to get in kilograms. And for me to do that, I'm going to use the molecular weight of water, right? So my mass in kilograms, I'm going to do, I have 3 moles of water. And I'm going to multiply this by the molecular weight of water. Okay, so that cancels out my moles. And then now I need to do, I need to get this into kilograms. And so I have 1,000 grams is 1 kilogram. And when I get all of that, I get that this is going to be 0.0054 kilograms of water. 0.0054 kilograms of water. Okay, so I have my mass now. Let's go back up to this equation. I have the mass as 0.0054 kilograms. I have delta T is 5, and I have the CP. So I'm ready to calculate this guy. This is 0.0054 kilograms of water times 4.184 joules per kilogram Kelvin times 5 Kelvin. But that's not great. Sorry about that. 5 Kelvin. And then look, I cancel out my Kelvin like I promised you. I cancel out my kilograms like I promised you, and I'm left with joules. When you punch that all in, you get that Q is 0.11 joules, and that is your answer. This is the heat involved here. This is how much heat you need to heat up 3 moles of water from 10 degrees Celsius to 15 degrees Celsius. That's what we just calculated. All right, so that was transferable energy. That was heat. That's stuff that's not really useful for us. We often want to use stuff that is useful for us. So, because this is going to be a human-centric concept. We can harness heat, and we call that work. And that's our own invention. It's a human-centric invention. We can harness the heat and do something we want to do with it. So, as the first examples of us doing stuff like this were watermills. So you had a river flowing, and you put some watermill in the middle, and that thing would spin. And by the sheer movement of the water, you can harness the energy of the river and do stuff with it. Which was pretty useful back then. Another one would be if you have mules pulling on yokes, and they would spin around and around and around, and you can harness the energy to do something useful for yourselves. That is usually involved with someone moving things or something moving things. All right, and work. You have energy of movement. We can calculate that by force times distance. You can have an expansion work. So if a gas is expanding in a piston engine or something like that, it's the pressure of the gas times the delta volume that's expanding or contracting. And there are other types. There's a lot of types of work. That you can, there's the nuclear work, surface work, and all these things. But I'm just showing you the 2 common ones. Okay, this is again, it's the same stuff as heat, but heat is not useful to us humans. It's just something that's dissipating, like friction. We can't really do anything with it. But if we can harness it, then we can power things like simple devices or simple processes, and that's the whole idea behind, say, batteries or electricity. It's basically us harnessing this heat that's already transferring from place to place, and might as well use it.